is that a screwdriver?
Mike Cavazula.
And Gustavo Chen.
And we did a similar project, this Digital Christmas Tree Ornament. Basically what as the other team talked about, basically what our project is it's a digital photo frame that's modular that you can hang from a tree during Christmas time to display pictures. There are a couple design constraints, obviously, since it's supposed to be small and lightweight. We're also looking for a cost-effective design and a low-power design so that it can be powered on as long as possible. Finally, it needed to be standalone. That kind of went hand in hand with the low-power thing, since we weren't going to use like an AC connection or something like that hooked up to the wall. It had to be completely standalone, no external inputs while it was operating. Here's some pictures of our project. There it is in the case up there on the left. Here's with the battery case open. We actually brought it today. I'm going to pass it around. It has a touch screen. There's a power button on the side. I ask you not to turn it off. The touch screen isn't as sensitive as I might like. So if you press it and nothing happens, just press it a little harder.
It's pretty user-friendly, as you'll see.
So it's scrolling through the main slideshow program right now. If you press onto it, it'll bring up a menu with a bunch of different features that you can, mess around. Here's the main system level block diagram with the hardware that we use. The main single board computer we're using is the Gumstix Vertex XL6P. This hardware is really nice because it's completely modular. You can add, there's a whole bunch of different boards that connect onto it in a stacking fashion to add different functionality. Our particular implementation uses a micro SD reader as an add-on card, as well as an LCD controller. So it's actually the main board and two expansion boards on top and below it. Like I said, what's really nice about the design is you can add additional functionality to it. There's an audio controller if you wanted music or something. There's a Bluetooth controller. There's really a whole bunch of things that you can add on this to increase so that you can do more with it. Okay, now we're going to talk about the major subsystems in the project.
Hello, I'm briefly going to talk about the power research and development. In the beginning phases, I looked at many power options. Some of them included an AC power source that would connect directly from the device into the AC source. That would also have to have a transformer on the side of the device. I've also looked at power options such as lithium-ion rechargeable batteries, industry standard AA, AAA, and quadruple A batteries, and also a 9-volt replaceable battery. So as far as the implementation is concerned, during the power implementation, I tried to look at all the different power options and sort of compare different power options in terms of size, compactness, cost, weight, etc. So during this research, I came to a resolution that the best option to power on the device for the longest amount of time would be to use 4 AA batteries. And once again, as I said, I compared the cost versus compactness versus other types of options. And one more thing I'd like to mention is that the overall device is an onboard voltage regulator that basically allows you to convert, down convert, or up convert voltage anywhere between 3.6 volts, which is the cutoff voltage of the main board, and up convert it to 6 volts, or down convert it back to 3.6 volts. And this is one of the applications that I ended up using, and I will speak of this later as well. The basic testing, once we had the power option set up, I basically went into the lab and I used a software called LabVIEW in order to connect the device to the multimeter, which was connected to the computer. And this LabVIEW application basically monitored voltage versus time, draws from the entire system, or current versus time. In our case, I ended up just using voltage versus time. And basically, I had a couple of curves. I did 12 tests in total that had power utilization of the entire system, from the initial boot up to the cutoff voltage, which was at 3.6 volts. As far as the functionality of the system, our basic requirements, the unit was intended to operate for a couple of hours a night for a couple of nights, after which point we would have to replace the batteries. The basic after I did all the tests, the functionality showed that the actual system operated for over 7.5 hours, which was just remarkable compared maybe to the other team that ended up using it for about 3 hours. I mean, once again, we had 4 batteries, and that was also the case. Sorry.
We were able to, our original board came with Linux, but we were able to reflash it with an open source Windows CE operating system, which made it real nice for development. We were able to use the .NET conflict framework, so we were able to develop on the computer, and then use debugging features within Visual Studio and on the unit itself. We also at first had a problem with overflow errors because we had to convert images into bitmap, and when bitmap's a very large file, it would eat up all our memory. So what we did was we found an open source image wrapper, which would take any size image and scale it down to the size that we needed, and then create the bitmap, which would make our file sizes much smaller and much more useful.
One of the nice things also about the Windows CE operating system, initially under the Linux operating system that we used, there weren't, at the time when we were developing, there weren't any drivers available to drive the touchscreen. There were drivers available under Windows CE to drive the touchscreen, and that kind of reshaped our design process.
Right now, we're able to support JPEG, PNG, GIF, and bitmap files, which can be loaded on directly from the unit. We can also sync from sync to the unit using Microsoft's ActiveSync through a standard USB. Currently, we're loading on images directly from the onboard micro SD card. It scans through the entire card and loads on any image on the card into an array, and then renders directly on the unit. So there's really so the whole unit's pretty much standalone. So you can run the whole unit without ever actually connecting it to a computer, which is real nice. And also we're able to downclock the processor while we're rendering any images. We try to do it as fast as possible. But once they're loaded onto the main memory, we downclock the processor because it really doesn't need that much power, that many clock cycles to just transition through the images. So as far as our GUI, we wanted to make it very simple and intuitive, so any non-technical user could use it very easily. Now, the final implementation, we have an initial loading screen which loads on the first 10 images, and then so just to cut down on start time, and then later on during the slideshow, any more images that happen to be on the card render at that point. And it's completely self-sufficient. So as soon as you turn it on, you could just let it go and not touch it, and it'll run for however much time.
When we were processing the images, we implemented an image queue. For a small number of pictures, less than 200 about, we can actually load every single picture, the thumbnail, the small one that's displayed on the screen, into main memory. And that greatly speeds up load time and transition time and things like that. For a large number of pictures, it'll keep roughly the 200 pictures in main memory, and then it will have a cycle where it loads pictures into main memory ahead of time, so that it eliminates stuttering as it processes new images, since we do process images directly on the unit.
Yeah, we were able to fill many of the subsystems, all of our customer requirements, as well as a few other features that we thought would be nice. And then this is just a block diagram of our GUI. As you can see on the left, the main portion is a slideshow. Oh, okay. Okay, so as soon as you click, you get a stationary picture, which gives you the option